electric potential energy. You're probably going to want your formula sheet out. You're definitely going to want your formula sheet out. We're going to define electric potential energy in a manner similar to cosmic or orbital gravitational potential energy. We're going to say that electric potential energy reflects the work that must be done to move a negative object, little q. Let's put a little negative right there, from a point near a positive charge, big Q, let's put a plus sign there, out to infinity. So if I wanted to move this negative charge away from big Q all the way out to infinity, it wants to fall back towards Q, I would have to tug and apply a force. Although the further away I got, the easier it would be to pull. And in fact, all the way out at infinity, how much force would there be? 0. So what would my potential energy be all the way out at infinity? Well, since I could let it go and it wouldn't fall, 0. Similar to that relative to 0 at infinity for cosmic potential energy. Or the other way to think about it, don't write this down, if this was a positive charge, it would be how much work if I started at infinity and tried to push it inwards. So if I was starting with a positive charge, because like charges, I would have to be pushing and pushing, and the closer I got, the harder and harder and harder and harder I would have to push. I would have to be doing work, because if I let it go, it would want to fall. I would be adding energy to it. Recall that the force between two charges is not constant. It varies with difference. It's K big Q little q over r squared. Because of that, I can't just go, oh, work equals force times distance. It's a changing force. Once again, I would sketch a curve and I would use calculus to find the area underneath the curve, but I'm just going to give you the punchline. The potential energy between two charges, electric potential energy, is K big Q, little q over r. Or KQ1, Q2 over r. You might compare that with gravitational potential energy, which was big G, big M, little m over r, but negative. And you'll notice, Lorenzo, they kind of look the same, similar. Constant there, a constant there. Charge, when we're talking about electricity, seems to behave mathematically really similar to the way mass behaves when we're talking about gravity. Not an r squared, not an r squared. What's the big difference that you notice between the two of these? This one also has a... Why doesn't this one have a negative? Well, for masses, the charges always fell towards each other. And so we put the negative in. When will charges fall towards each other when we're talking about charges? When the charges are like or unlike? Okay, you know what we're going to do? We are going to, in the actual equation, just include the plus or minus of the charge. And that's why if you look on your formula sheet, I did not put absolute values around these Q's, I don't think, did I? If they're unlike charges, you'll put a plus and a minus in, and that will give you a negative answer because they want to fall towards each other the same way gravity wants to fall towards each other. If they're like charges, both negative or both positive, you'll still put the signs in, and you'll get a positive times a positive, positive, or a negative times a negative, a positive, and that will give you a positive amount of potential energy, which works because what that is saying is if you let it go, it wants to fall already. Yeah. So our workaround here, I used to make kids memorize this, and so I would say something like this for forces and fields in the first line on your formula sheet. We forget the signs. Now I put absolute value signs around them. I'm mellowing in my old age. And then I used to say to the kids, for scalars, like energy, we include the signs. Well, I'm nicer now, Trevor. It's on your sheet. If I didn't put absolute values, that probably means you can put the plus or minus sign in there. Okay. By this relationship, potential energy is still 0 out at infinity. Calculus students, if you take the limit as r approaches infinity, you'll get 0. by this relationship, unlike charges, have negative potential energy, which makes sense because if they have negative potential energy, to bring them out to zero where they don't want to go, you'll have to add energy. You'll have to do work. Something like example 1. Example 1. Example 1a says, find the potential energy of a negative 75 microcoulomb charge that is 3 centimeters, nice try, 0.03 meters, from a positive 120 microcoulomb charge. Okay. Kimia, what's A asking me to find? Is it asking how much work? Say no. Is there a change in height, change in speed? This is a job for conservation of energy. Say no. This is just saying find potential energy, which is K, big Q, little q, over R. Now, common sloppy mistakes. Kids have found force so often that they'll write an R squared, even though the formula doesn't say so. Don't do that. What's K? Anyone, what's K? Okay. Big Q, that's the fixed charge that's not moving, and we will assume that these are like glued to the paper or thumbtacked in place or something. It's going to be positive 120. What was that mu? Oh, that was microcoulombs, which was 10 to the what? What's little q? Not 75, negative 75 microcoulombs, all divided by 0.03. This should work out evenly, I'm pretty sure. In fact, I know it will. How much potential energy is stored between these two charges? Trevor, what'd you get? I recognize that fleeting look around of terror. Trevor, do you have a smart device here of some type? Well, that's not so smart. Can you power it off, please? I didn't do this in my head. I'm going from memory. It's negative 2,700. Yes? Okay. Is that all right, Aisha? Yep. Yeah, you lying? Okay. What's B want me to find? Well, it says write a work energy equation. I think it's going to be a work equation. Why can't I just go, don't write this down, work equals force times distance? Why can't I do that? Anyone? The force is changing. By the way, it's such a pain to use the longer version of work that in a couple of days, we're going to go hunting for a situation where the force doesn't change, where the electric field is constant, and where I can go force times distance. And we're going to go, oh my goodness, 1 line instead of 10 lines. We will find such a location, but for now, I have to use change in potential plus change in kinetic. Honestly, if all B says is write a work energy equation, you're technically done. That's the work equation. We can go a little bit further, though. I think it says that we can assume that the charge begins and ends at rest. Does it not? I did say that, yeah. So we can go, haha. Ethan, what's C want me to find? The actual work. Okay. Well, it's the change in potential. Ethan, what's change in anything? So this is going to be potential energy final minus potential energy initial. Not MGH. This is not height potential energy. This is electric potential energy. It's going to be K. Big Q. Wait. What's my final location, Ethan? All the way out at? How much potential energy do I have out there? Oh, for Pete's sakes. I'm going to do that. And in fact, I'm going to get 0 minus negative 2,700. Ethan, I'll bet you can even do this in your head. What's a minus minus the same as? and I end up with how much work will I need to do if I want to get this charge out there? I'll have to add 2,700 joules to its original negative 2,700 joules to get it to zero, to get it to infinity. Now, I could also, instead of saying out to infinity, I could have given you a second R final, and this term wouldn't have canceled, and you'd actually have to crunch each of these and actually do the subtraction. Meh. Moderately more typing. Turn the page. With this potential energy equation, Hannah, that also means that like charges will have positive energy. Well, yeah, because if the charges are like charges, if you let them go, they'll start to move on their own. Thank you very much. They must have some potential energy to spare because they're going to be repelled. Example 2. Find the work required for an external agent to place a blah blah charge 5 meters from a fixed charge. Assume it's initially at rest an infinite distance away. Okay. Oh, and it begins and ends at rest. Wants me to find the work. Can't go force times distance. So I guess I'm stuck with going work equals change in potential plus change in kinetic. Oh, they said starts and ends at rest. Woohoo! What's change in anything? Final minus initial. I guess this is going to be K, big Q, little q, over R final minus... What's my initial potential energy? Where am I starting out at? So what's my initial potential energy? So it's going to be 9 times 10 to the 9th. The fixed charge is usually what I put in for big Q because it's the planetary charge that's stuck there. It's positive 1.75. It's not micro, it's a lowercase m. Oh, milli. What power of 10 is milli? Oh, times 10 to negative 3. And then the moving charge is 2.5 positive times 10 to the negative 3 divided by 5. This will probably work out evenly. I can't imagine that 2.5 divided by 5 won't give you a nice number. I don't think you'll end up with a long, non-repeating, non-terminating decimal of some type. $7,880 joules. And then as soon as you let go, this would start to fly up and it would start to lose that energy because it would want to reach back to its stable state of 0. It would fall up. But otherwise, do you notice, Danielle, this is looking an awful lot like gravity. Although the numbers are nicer. It's much nicer to work with 9 times 10 to the 9th than it is with 6.67 times 10 to the negative 11. So for energy, which is a scalar, we're going to include the positive or negative charges in the equation. Unlike forces and fields where we forget the signs, we decide the direction for those by using like charges repel, unlike charges attract for forces, or by asking which way would a positive at this location want to move if it could for electric fields. Now, in both of these last two questions, we had an external agent, maybe an invisible angel or leprechaun or something, moving the charges around. If there is no external force, well then, energy will be conserved because there's no outside source of energy. Example 3, an electron is originally 2 points that far from a proton and at rest. I would probably underline the phrase at rest. It's released and moves directly towards the proton. I agree with that. Find its speed when it is that far from the proton. Chloe, what does this want me to find? How much work? Sure, no. What does it want me to find? starts here and it ends here. Is there a change in height? There is if I turn my head sideways and imagine that height is in this direction. Is there a change in speed? Is there a yucky, curvy force? You know what this is a good job for? Anyone? Conservation of energy. See how I put that all together, Chloe? They didn't ask how much work, but there's definitely some movement going on here. Change in height, change in speed, curvy force. So the first thing I'm going to write out is conservation of energy. K E initial plus P E initial equals K E final plus P E final. Are any of these zero? Let's do kinetic first. Is there ever a time when it's at rest? One. Oh, initial? Okay. What about potential energy? Where would potential energy be zero if I was at what location? Am I ever at infinity? Now, I could make this question look tougher, but be easier by saying, assume we start out at infinity. A lot of kids freak out. I don't know what to do. Oh, no. That would mean that your initial was zero. That'd be way easier, but I did not do that. So let's expand these. Potential energy is going to be K, big Q, little q, over R initial, and this equals a half m v final squared plus K, big Q, little q, over R final. Chloe, what am I trying to find? I would not try and get this by itself right now. What I am going to do is I'm going to minus this over to that side and just get a single number on the left. In other words, my next step would be to rewrite this as K, big Q, little q, over R initial minus K, big Q, little q, over R final. That equals a half mv squared. And Grace, what I'm going to do now is I'll get that as a number, then I'll times by 2, divide by m squared root. What's K, Chloe? Good. Big Q. It's a proton! It's pretty elementary to figure out what the charge is on a proton. And I'm raising my voice on purpose and doing that yell on purpose because one of the things that I do get annoyed at is if in the future on a quiz or a test, hint, hint, I give you a proton or an electron to deal with and you say, you didn't give me the charge or the mass. No, it's a proton! It's on your sheet. What is the charge of a proton? Positive or negative? Because signs matter now. Positive. I'll put a plus sign in my notes so you don't need to. 1.6 times 10 to the negative 19. Charge little q. It's an electron! Also pretty elementary to figure out the charge of an electron. What's the charge of an electron? Negative 1.6 times 10 to the negative 19. All over. What was R initial? I've scrolled down. Pretty small. Minus. Hey, wait. Is this K the same as that K? Is this Q the same as that Q? Is this little q the same as that? I'm using ditto marks, baby. Ditto mark times ditto mark times ditto mark. What was R final? That equals a half m v final squared. Yeah, because I think I'm going to be able to do my backspace and edit trick again. I hope. So I'm going to carefully type in the first one. 9 times 10 to the 9th time. Ooh. Ha. Ready? I notice I got a 1.6 and a 1.6. It's going to be negative. And because these charges happen to be the same, then I could just go squared. Come on, that's pretty good. Divided by 2.5 times 10 to the negative 11. That trick is only going to work if your two charges happen to be identical, but I'm lazy enough that I'll use it. And I'll write down the whole thing, not round it off. Negative 9.216 times 10 to the negative 18. negative 9.216 times 10 to the negative 18 minus, and then I should be able to just backspace 1.0 and edit, and I get, yell at me if I'm wrong, but I'm getting negative 2.304 times 10 to the negative 17. That equals a half m v squared. Let's carefully crunch this. It's going to be negative 9.216 times 10 to the negative 18 minus, answer button. Double checking my typing. Looks good. Do you all get 1.3824 times 10 to the negative 17? Those there?
Yes.
What did I call that on that line? What did I call that? The something charge. Is that why I keep saying it's pretty elementary to figure out the charge on a proton or an electron? Did Hannah just get the joke now? That's okay, at least you got the joke. There's some people here, zing, over their head, right? By the way, Hannah, in all honesty, I'm glad you asked, because you aren't the only one that wasn't sure, and so good. By the way, do you notice also on there are some masses? That's a hint. Good. I was actually going to call you out in a positive. I was going to say, I see you looking at your formula sheet. I think Hannah's looking ahead to figure out the mass of the electron because she sees an m in the equation. It is all on your sheet for the protons and for the electrons. I will not give you those in the questions. I gave them to you on your formula sheet. Meanwhile, do you all get 1.3824 times 10 to the negative 17? 1.3824 times 10 to the negative 17. That equals 0.5. You know what? Let's go. A half m v final squared. Now, how would I get the v by itself? Times 2 divided by m. Which m? It's an electron. It's on your sheet. I remember that the electron is 911. It's 9.11. It's 911, but I can never remember the 10 to the. Okay? So, v final is going to be the square root of answer button. I was actually lazy enough to write ants. 1.3824, that. Divided by 2 times 9. No, times 2, Mr. Dueck. Or divided by 0.5. 9.11 times 10. You said negative 31, Ben? Yeah. 2 times answer button divided by 9.11 times 10 to negative 31, and holy smokes, that's faster than light. Oh, I forgot the square root. And that's something kids have done in the past. They're giving me an answer. Speed of light's 3 times 10 to the 8th. Please don't be telling me the electrons or protons are traveling faster than that. But for what it's worth, typically electrons, if I give you a question, they're going to be traveling in the 10 to the 5th, 10 to the 6th, 10 to the 7th range. They're going to be hauling. Because electrons don't have much mass, it's pretty easy to get them up to a pretty high speed. 5.51 times 10 to the 6th, I believe. Meters per second. Now, the other thing that I could have done, Justin, is instead of saying, here's where we started, here's where we ended, how fast, I could have told you how fast, and either where we started or where we ended, and asked you to find the other r. We'll do one like that later, because that's on the bottom of a fraction and it's a bit yuckier. Example 4. How much potential energy does the negative 1 microcoulomb charge possess? Okay. What's the first thing that I would do here before I even bothered diving in? I think with 3 charges. Sometimes I'm a bit lazy with 2. You notice in the previous questions, I just assumed big Q, little q. But yeah, if there's 3, I'll call this Q1, Q2, Q3. So which charge, Lorenzo, does it want me to find the amount of energy of? Q1, Q2, or Q3? Here's what I'm going to do. Don't write this down. I'm going to find how much energy those two have, and I'm going to find how much energy those two have. It is true that these two also have some shared energy. I don't care, because that's not what they asked me. Okay? Now, if they had said find the energy of the whole system, then I would also have to calculate that. So I'm going to find the potential energy between charge 1 and charge 2, which is going to be K, Q1, Q2, all over R12. Oh, not squared. Good yawn, Aisha? Breathe. Good yawn? Yeah. What's K? Good. Q1, positive 5 microcoulombs. Q2, negative 1 microcoulomb. All over, not 2. What's R1? 0.02. Pretty sure this will work out evenly. It should. What do you get? Negative 2.25 joules. Anyone else? Yep. Negative 2.25 joules. As I said, because K is 9 times 10 to the 9th, you often have much nicer answers than we did with all the gravity stuff. 6.67, not much stuff goes evenly into that. Now I'm going to find the potential energy between charge 3 and charge 2. I'm feeling bold. I'm going to see if I can go straight to numbers. It's going to be 9 times 10 to the 9th, negative 2 microcoulombs, negative 1 microcoulomb, all over 0.04. You know what? I'll bet you can backspace and edit your previous one and just change the 5 to a negative 2 and the 0.02 to a 0.04 and save yourself some typing. This is smaller, and this is... You're going to get a much smaller answer than negative... First of all, you're going to get a positive answer. I think less than 1, but I'm not going to give you much more than that. Sorry? Positive 0.45? Okay. That's the potential energy between those two. That's the potential energy between those two. Now what? What am I going to do with those two answers? Louder, I couldn't hear, sorry. Draw them tip to tail? Is energy a vector? So do I need to go tip to tail if it's not a vector? Are you saying that I put this right-angled triangle in there just to suck you in and see if you were willing to actually go tip to tail and now do some trig? Yeah, they used to love doing this on the provincial exam. In fact, if they were feeling really nasty, instead of making it a right angle, they would have put this charge right there and actually given you an angle theta, and kids would have started pulling out like the sine law and the cosine law and just ended up going down this black hole of darkness, and that would have been a multiple choice answer to pick. Probably answer A. Fact, I can probably do this in my head. You want the total potential energy? It's going to be negative 2.25 plus 0.45, negative 2.2 plus negative 1.8? It was an old provincial exam mean trick. For scalar questions, they would give you nasty diagrams and see if kids would start diving into the tip-to-tail trig. Don't need to. In fact, that's why we were able to use conservation of energy to analyze roller coasters, because roller coasters had constantly changing hill angles. Scalar. I like example 5. I like example 5. I like example 5. Example 5 is a nice question. An electron. It's an electron. An electron starts out 3 meters to the right of a fixed charge. If it's moving towards the charge at 4.6 times 10 to the meters per second, how close will it get before it comes to a stop. Hint, DULP. Matthias, you probably haven't seen this. Everybody else, what does DULP stand for? Draw a little picture. It's an acronym. Okay, the electron's to the right here. So here's the fixed charge. Let's put it right here. Big fixed charge. It's negative 5 microcoulombs. Here's the electron. Symbol for electron is E negative. Now, normally, which way would this electron want to move because of that guy? It's going to get repelled. But we've given it a big push. It's traveling this way at an initial speed of 4.6 times 10 to the 7th. And it started an initial distance of 3 meters away. As it gets closer and closer and closer, what's going to happen to its speed? Yeah, because it's getting repelled more and more and more. I'm just going to make a ballpark guess. Maybe right there is where it comes to a stop. And they would like us to find R final, when V final equals 0. Got the argument okay? Is this question asking how much work? No? Okay. Oh! Is there a change in height? Is there a change in speed? Is there a yucky curvy force? You know how I'm going to handle this? Conservation of energy. So I'm going to have KE initial plus PE initial equals KE final plus PE final. Are any of these 0? Oh. If I was nice, instead of starting 3 meters away, I could have said we'll start a very, very long distance away, which is meant to imply infinity. We could have said initial potential was 0. I'm not nice. All right, let's expand these. Kinetic, Mr. Dueck. A half m v initial squared plus k big Q little q all over r initial equals k big Q little q all over r final. Justin, what are they asking me to find here? Which is which variable in this equation here? Give you a hint. It's one of the r's. And oh yeah, sorry, I didn't hear the f each time. Yeah, r final. You know what? It's on the bottom of a fraction. I'm not going to try and get it by itself yet. You know what I'm going to do, Justin? I'm going to turn this into one number first. I'm going to crunch all this. And then when I have one number equals this, then I'll get the r final by itself. So here we go. 0.5 m. It's an electron. 9.11 times 10 to the negative 31. V initial, I've scrolled down. I think it was 10 to the 7th, but I can't remember the what. 4.6 times 10 to the 7th. Don't forget the squared. It's amazing how often kids are so proud. They've come so far. They're writing everything out, and they forget the squared. A few of you are smiling, bringing up past memories. Plus 9 times 10 to the 9th. Big Q negative 5 times 10 to the negative 6. Little q, Hannah, it's an electron. Can't be 1.6 times 10 to the negative 19. It's an electron. Negative. All over, our initial is 3. I'm a math nerd. I have to complete the equation, but I've run out of room. So I'm going to go equals ditto mark. The right-hand side just dropped down like a domino, but I don't have room to fit it on my page right now. So that's not equals 11. That's equals same thing. KQ, Q over RF. Alrighty, let's crunch some of this. a half m. Do you have some of these, Danielle, programmed in, these masses as well? Yeah, there you go. You might find on your third or fourth sig fig your answers might be different from my answers, but I'll be okay with that. For the kinetic energy, do you get 9.63838 times 10 to the negative 16? And I'm going to carry this whole thing. I'm not going to round off. 9.63838. 9.63838 times 10 to the negative, what did I say, 16? Plus 9 times 10 to the 9th times negative 5 microcoulombs times, it's an electron, divided by 3. Double check my typing. Looks good. Oh, you get 2.4 times 10 to negative 15. That equals ditto mark. So that number plus 9.63838 times 10 to the negative 16, I get 3.363838 times 10 to the negative 15. 3.363838. 3.363838 times 10 to the negative 15. Now I'll write the rest out. Equals K, big Q, little q, all over R final. Justin, what did you tell me this wants me to find? R. How would I get the R final by itself now? I think, yeah. I'm going to multiply it to there, and I'm going to divide this down there. So I'm going to write R final equals K, 9 times 10 to the 9th, Q, negative 5 microcoulombs. Little q, it's an electron, all over answer button. How many of the calculator lets you go back 2 lines? Okay, those of you that do, I typed almost all of this in 2 lines ago. If I go back 2 lines, I get the 9 times 10 to the 9th and the negative 5 and the negative 1.6. In fact, all I need to do, I think, is replace the 3 with my answer button, and I can save myself a lot of typing. Learn how to make your calculator sing. And it was last unit and this unit that I had in mind when last year I kept going on all those calculator rants. You get 2.14 meters. And that makes sense. It should be, I knew it was going to be less than 3. If I got an answer bigger than 3 meters, I'd be saying, no. It's getting closer, not further. .14 meters. I got a video to show you, but first I'll tell you which homework questions that I assigned. You can try number 1. Now, in number 1, part C, you're not going to need to add them tip to tail, but what you're going to do then, Josh, is you're going to find the potential energy between those two. Josh Jacob, wow. And the potential energy between those. I got the J right. I'm getting old. Good gosh. You're going to also find the potential energy between those two, but to do that, you'll need that distance, and that you'll need to use Pythagoras for. 50 squared plus 50 squared equals square root. Okay? But then that'll tell you the whole energy of the system. 2. 3. 4. 5. He's going to assign them all, isn't he? No, skip 6. Skip 7. 8. So what did I assign? 1, 2, 3, 4, 5, 8. Is that correct? Okay, let me put that on your copy because this is the copy that's going to go online, Mr. Dueck. 1, 2, 3,